Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 2.7, day 2, entitled One-to-One Functions and Their Inverses. And today we're going to talk about these last two objectives. We're going to talk about how to find the inverse of a function, as well as graphing the inverse of a function. Now the inverse of a function, we've talked about it yesterday. If a function is one-to-one, that's important because the function that you do to go from the input to the output will also work backwards when you're trying to go from the output towards the input. So the definition here for our inverse function says that we want to let f be a one-to-one function with domain A and range B. And then the inverse function, we're going to write it as f to a little -1 power. That's how we write the notation for an inverse. And that inverse function is going to have domain B and range A. So you're basically switching the direction that the function is operating in. And this is a really good picture that shows that concept. If your original function goes from A to B, then the inverse function goes from B to A. And you're going from that same input value to the range value, and that same range value back to the original input value. So, in example 4 here, this is just to conceptually make sure we have a grasp of what this inverse is really asking us to do. We have three functions. We have f of 1, which gives us 5, f of 3, which gives us 7, and f of 8, which gives us -10. Now this could be all the same function, could be three different ones, doesn't matter. But if they tell us to find f to the -1 of 5, remember again, this means to find the inverse. That f to the -1, that -1 exponent, now when it's written with that function notation, that tells us to find our inverse. So find the inverse of f of 5, f to the -1 of 5. So that means they want us to start at 5 and go back. So we would have a value of 1. So find f to the -1 of 7. So I would be using this function here. I'd be putting 7 into the function and working backwards. So that would give me a value of 3. Part C, find f to the -1 of -10. So that means I'd be working with this function here where I'd start at -10 and work backwards to give me a value of 8. So again, this example just reinforces that if one function goes from one input to an output value, then the inverse of it will take you from the output back to the original input. Now, we can actually find the inverse of a one-to-one function algebraically. And we're going to write the equation with replacing y for f of x. So that's our first step. Now, the second and the third step, I want you to flip-flop. I don't really like how the book has them ordered here. Okay? So what we want to do is we want to rewrite the equation so that we have y equals whatever it is. Then we're going to switch the x and y values. You're just going to switch those variables around, basically. You're just going to make all the x's y's and all the y's x's. And then you're going to solve the equation. And then we're actually going to be solving for y, not x. Okay? So as we go through our next example, I'll illustrate those steps a little bit clearer than what was in the chart in your book. So for example 6 here, they want us to find the inverse of f of x equals 3x minus 2. So I'm going to rewrite it as y equals 3x minus 2. What I'm going to do is replace that f of x with a y. So that was my first step. Then I'm going to switch the x and the y. I'm literally just going to switch them. So where there's a y, I'm going to put an x, and where there's an x, I'm going to put a y. And now I'm going to solve the equation for y. So I'm going to subtract the 2 over. Oh, I'm sorry, add the 2 over. And then I'm going to divide everything by 3. So I'll have y equals x plus 2 over 3. Now my very last step is to rewrite it with my function notation again. And so since this is my inverse, I'm going to rewrite it in my inverse notation. So x plus 2 over 3. So again, instead of just leaving this as a y, I'm going to replace it with f of x, kind of like what we did up here. We changed the f of x to a y, but now that this is my inverse, I have to use the f to the negative 1. Okay, so the original function was 3x minus 2. To completely undo that, we want to add the 2 and divide by 3. Should make sense. To undo subtraction, we add, and to undo multiplication, we divide. So here's another one. Find the inverse of this function. Now this is a little more complicated, but we're going to follow those same steps. I'm going to replace the f of x with a y. So y equals 2x plus 3 over x minus 1. And then I'm going to go through and I'm going to swap out all the x's and the y's. I'm going to flip-flop them. So I'll have x equals 2y plus 3 over y minus 1. Now, since this is an equation, I could think of it like a ratio. One fraction is set equal to another fraction. So if I'm going to try to start solving this for y, I would cross multiply. That would be my preferred method. So I'll have x times y minus 1 equals 1 times 2y plus 3. And I do need to distribute here, so I'll have xy minus x, and then just the 2y plus 3. Now I'm trying to solve for y, so I've got to get all the y's on the same side of the equal sign. Doesn't matter which side you get them on. I'll just subtract the 2y over here, and then I'll add the x over to this side. I'll finish my work over here. So now I'm going to have xy minus 2y equals 3 plus x, or x plus 3. Now here's the step where students usually have trouble. We're trying to solve for y, and they see 2 y's. We want 1 y. So basically, I need to recognize that these two terms have y in them as a GCF, and I'm going to take it out. So I'm going to take out the y and be left with x minus 2. So it's kind of like I'm undoing distribution in a way. And now I have 1 y that I can finish solving for. So I have to divide by the x minus 2. So y will equal 3 plus x over x minus 2. And I'm not quite done. Remember, we have to rewrite it in our function notation. So this will be f to the negative 1 of x equals, and then if you wanted to be consistent with your formatting of your variables, you could do x plus 3 over x minus 2. So that way you have your variable first and then your term, your constant term. Doesn't matter. You know that you can add in any order. I wouldn't mark it wrong if you had 3 plus x and I had x plus 3. It's the same thing. But please do not forget that last step where you have to rewrite your final answer back in that function notation. Okay, now here's another cool little thing that happens when you have functions that are inverses and when they're one-to-one. You can take your composite functions and you can put one function into the other and you'll get x. And it doesn't matter what order you do that in. So you can do your fog, your f of g of x, or you can do your goff, your g of f of x. Whichever way you substitute one function into the other, doesn't matter, because when they all simplify down, you get x. So that's one way to tell if two functions are inverses. You can put one into the other and see if you get x. If you get x, they're inverses. If you don't, they're not inverses. Now in example 6, we had our original function was f of x equals 3x minus 2. And then our inverse that we found was x plus 2 over 3. So I'm going to demonstrate this concept of putting a function into a function and getting x. Okay? So I'm going to take this function here and put it into the other one. So I'll have 3 times x plus 2 over 3 minus 2. Now remember, here when I'm multiplying, this 3 is over a 1, so those 3's cancel. So then I have x plus 2 minus 2, which is x. Look at that. And you could go the other way as well. You could put the f of x into the f to the negative 1 of x. If you really wanted to, I can show you that. We would have our 3x minus 2 plus 2 all over 3. And there, the 2's would cancel, so you'd have 3x over 3, and then the 3's would cancel, so you'd get x. Okay, so there's a demonstration of the Fogg and the Goff concept. It doesn't matter what order you put one function into the other. If they're inverses, it'll all simplify down into x. You should have seen that last year in Algebra 2. Okay, so now we're going to graph some functions. And basically, when you have inverses, this middle part here of this slide is getting at the main point here. When you have your original function, you're going to have some ordered pair in it that's AB. And if your functions are inverses, then the inverse function is going to have a point that's BA. So the domain of the function has to match the range of the inverse, and vice versa. So you're basically flip-flopping all your ordered pairs. Okay? And what happens when you do that, when you have your original function, here we have the blue f of x function, and then we have our inverse in the red, so that's the f to the negative 1 of x. They're inverses of each other. So we took all the ordered pairs of f and we flip-flopped them, and that's how we got all the ordered pairs for f to the negative 1. And when you graph them, inverse functions are always going to reflect across the equation y equals x. And that y equals x, that's our diagonal line that starts at 0, 0, and then you have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, etc. So that's a characteristic that's important to remember when you're graphing functions. If you're graphing functions that you know are inverses, that line, y equals x, that diagonal line has to act like a mirror. If it doesn't look the same on one side as it does on the other, then either your equations aren't inverses or you're graphing improperly. Okay, so example 9 actually has 3 parts to it. We have A and B here, and then C is on another slide. But for part A, they want us to sketch the graph of f of x equals the square root of x minus 2. So again, you'd want to go to your graphing calculator. You'd want to make a table of values. So let's do x and f of x. I'll just write it over here. And if we want to pick nice numbers that we know we can graph easily, so we don't have any fractions or decimals, we probably want to start at 2, because 2 minus 2 is 0, square root of 0 is 0. So that would be the first value on our graph. If we put 3 in there, 3 minus 2 is 1, square root of 1 is 1. If we put 6 in there, 6 minus 2 is 4, square root of 4 is 2. And we could do one more, 11. 11 minus 2 is 9, square root of 9 is 3. Okay, so that would be some values that we could graph for our original function. And this original function, hopefully, you've recognized that it's going to be a square root function, so it's going to look like a parabola. It's going to open up on its side. And I'm going to shift my y-axis just a little bit when I graph this so that we have a little more room over to the right. And I'm actually going to move it down just a little bit too, so we have room up at the top. Okay, so I'm going to plot those points now. So I've got 2, 0, 3, 1, 4, 5, 6, 2, 7, 8, 9, 10, 11, 1, 2, 3. Okay, so there's my original function. It's a square root function. Looks like half a parabola opening up on its side. And then part B says use the graph to make the graph of f to the negative 1. So we want to do the inverse now. So I'm going to have x and then f to the negative 1 of x. And basically what I'm going to do is I'm going to take this table of values that I had and I'm going to flip-flop all my ordered pairs. So instead of 2, 0, I'm going to have 0, 2. Instead of 3, 1, I have 1, 3. And 2, 6, and 3, 11. That's super duper easy. You don't even have to put anything into your graphing calculator. And then I plot them. So 0, 2, 1, 3, 2, 4, 5, 6, and then 3, 11, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And there's my inverse. Now I'm going to do a quick little double check. Remember, those inverse functions are supposed to reflect around y equals x. It should be right there. So everything that's graphed in purple, it should look the same as everything that's graphed in green if you're thinking of that red line as a mirror. So yes, those equations or those functions definitely reflect across that line, y equals x. And there's the nice book graph. Looks a little bit neater. But again, you can still see that this is your y equals x, and they're reflecting. They look the same on one side as the other. They're very symmetrical. Okay, now part C says find the equation for f to the negative 1. So our original function for f was f of x equals the square root of x minus 2. So if I'm going to find the inverse function now, I'm going to replace that f of x with a y. And then I'm going to switch the x and the y. And then I'm going to solve the equation for y. So I have to get rid of that square root, so that means I'm going to square both sides. And remember, when you square a square root, that radicand pops out. And then I'm going to add the 2 over. So x squared plus 2 equals y. But again, I'm not going to leave it written like that. I'm going to rewrite it in my function notation. And I need to make sure that I use the inverse function notation. So I'm going to have f to the negative 1 of x equals x squared plus 2. That should make sense. The opposite of a square root is squaring. Opposite of subtracting is adding. So you are going to see some problems like this on your homework where they want you to algebraically find the inverse, graph it. So you're going to have multiple steps to some of these problems to really emphasize all of these skills that we're talking about. Okay, now this last example is a thinker. It says the function f of x equals 3 minus x squared is not 1 to 1. Restrict its domain so it is 1 to 1. And find its inverse. Okay, now I'm going to take a look at the inverses first before we talk about the domain. Okay? If I'm going to find the inverse, I'm going to swap out this f of x for a y. 3 minus x squared. Then I'm going to flip-flop the x and the y. And then I'm going to solve for y. So I'm going to subtract the 3. I'm going to divide by that negative 1. And then here's the problem. I have to take the square root of both sides. And technically, when I do that, I get plus or minus. So I'm going to have plus or minus the square root of negative x plus 3 equals y. Okay, now this is why it says that the original function wasn't one-to-one, because I have two values here for y. So every x that I put in, I'm going to get two values for y out. So the way that I restrict the domain so that I make this a one-to-one function is that I either work with all the positive values or I work with all the negative values. So my domain could be all the positive values, or my domain could be all the negative values. And if my domain is going to be all the positive values, then my inverse function will be, equals the positive square root of negative x plus 3. And if my domain's all the negatives, then my inverse function will be all the negative values for the square root of negative x plus 3. So this is how I would restrict my work. I'd either or my domain, I'd have to either work with all the positive values or all the negative values. And if I'm working with just the positives or just the negatives, then I'll have two one-to-one functions. But together, it's not. And if you need to think of this graphically, remember that square root function looks like a little parabola laying on its side. So I'd have all the positive values here and then all the negative values there. And if we did vertical line test, it's not going to be a function. But if I have just the positives, that passes the vertical line test. Or if I have just the negatives, that passes the vertical line test. So separately, they are functions, but together, they're not. Okay, so here's your set of homework problems that you can practice these concepts. A little bit longer tonight than the previous assignment, but we did cover a lot of material. This is definitely stuff that you want to work on and practice. Don't forget to rewrite your inverse functions in that function notation with the f to the -1. And if you have any questions, come on in before school and see me.